All right, today we're looking at section 3.4, concavity and inflection points. So the first picture I want you to take down is these four different examples of concavity. And you're going to try to explain what concavity is. This is an example of concave up, and the function is decreasing. The function is concave up, and the function is increasing, so on and so on. After you copy those down, you're going to come up with a definition for what it means to be concave up or concave down. Because I'm tired of telling you guys everything. Cool. The pencil sharpener is cool. All right, everybody see this? Page 186 due tomorrow. Tuesday. Okay, we're going to fill in these two definitions. We're defining what it means to be concave up or concave down. That's what's going to go in the slots. Okay, is there a student out there who has an answer? Is there one out there? Okay, Sam.
I was going to say the area bounded below the line is less than the area bounded above.
Ooh. Now,
But it continues to go down.
now, even though there's crosshairs here, we're not including those, you know. Okay. Say your definition again.
The word bounded might not be correct. But
Okay.
the area, keep using it.
Okay.
The area bounded below the line would be less than the area bounded above.
Oh, okay. So, meaning, as you go this way, this becomes less and this becomes more. Is that what you're saying? Okay. Is that a good definition for concave up?
Like in like a thinking-wise sense, yes, but then you also have to factor in activities in.
Well, you also have to consider that this is concave up, and it's just the opposite of that is happening. Okay? So for concave up and decreasing, maybe we could do that. I want one just for concave up. Just for concave up. Kendra?
Is this a continuous function or a closed?
Continuous. Assume that these are continuous and differentiable.
Can't you just look at the end of it and see if it's going over
Yeah, actually.
the... Oh, wait, so we're looking about concave.
Yeah. So right now, just look at the top two.
Can't you just look at this way the curve's facing?
Yeah, like it's easy to say it's.
Okay. Hold that thought on the first, second derivative for right now. Okay? Just look at it. How about that? This is like a bowl that's facing upward. It's a technical way to look at it. It's a bowl that's looking upward. There's actually one that's in there. If you reverse these two, this one and this is a happy face, it's concave up, and this is a sad face because it's concave down. Okay, so angry eyebrows. I can see them. Okay, yeah. Okay. Angry eyebrows are concave down. Now, we have multiple perspectives that we look at things. One of them is visually. If you can look at a function and you can identify the intervals where it's concave down because of the angry eyebrows, perfect. Okay? You owe that all to her. However, I need a little bit more of a technical way. Perhaps. Okay, I'm going to give you a hint. So this is f of x for every one of these. Okay? This is f. Is there anything that is happening with f prime that is, oh my gosh, that's right. This is the applications of the derivative section. Is there anything that's going on with f prime, okay, for concave up? Brendan.
F prime is x approaches infinity is 0. Or, no, on that one.
Yeah. Remember, it's got to work for this one and for this one to do concave up. Yes? It's the same sign as f. Well, I could draw one where the function is down below. Okay? F is negative. Okay? And, well, yeah. You know what I'm saying. We could go concave up. This function is concave up, and f is negative. So no. Yes?
For concave f prime is increasing.
F prime is increasing. We have a winner. Okay? All right. Now, let's consider this one first. Because this one's a little weird, but it still works. Okay? Okay? Do you see those slopes? I always liked, those slopes are increasing. So I'm going to put that on here. Slopes are increasing. Okay? Meaning that f prime is increasing. Okay? If you want to put numbers on here, I could just make up numbers. Ooh, that looks like about a half. This looks like about a 1. This looks like about a 2. You know what I'm saying? They're increasing. And we're going increasing as you go from, whenever we talk about that, we always say we're going from left to right. Okay? So what's the deal with this? How is that possible? This is still, the slopes are still increasing. But how is that possible? So here, as I go from here to here to here, okay, this one might be negative a half, this might be negative 1, this might be negative 2. Remember slopes. Notice your slopes as you go from left to right are increasing, even though they're all negative. To go from negative 2 to negative 1, you're increasing. From -1 to -1/2, you're increasing. From -1/2 to 1/2, you're increasing. So the answer to this one here, a function is concave up when f prime is increasing. What's your guess as to when a function is concave down? Angry eyebrows. F prime is decreasing. So don't take it from me or Ryan, let's test it. So by testing this one, we look at the slopes at each one of these as I go from left to right. And then I'm going to go from left to right here. It has to work on both cases. So I'm going to slap slopes on these. This is maybe -1/2, -1, -2, 1, probably 2, 1, 1/2 roughly. Look at the slopes. The slopes are decreasing. -1/2, -1, -2. They're going down. Okay, so it's weird when we talk about slopes being slopes increasing or slopes decreasing, because of the fact that the slope is also the change in how the function is changing. Okay. All right. If you didn't jot that down, something to that effect, do that right now. Now I want to show you some examples here of different functions. And step one of this whole phase is figuring out where the function is concave up and concave down. So let's take a look at that.
So with something just like a base x squared, would it be just concave up and that's it?
Absolutely.
No increase, no decrease?
Everybody hear that question? A function y equals x squared. That function is always concave up. Okay?
And just, that's it?
That's it. And we're going to actually prove why that is. These are the definitions. When we go to the next phase, we're going to define how do you determine that by just looking at the by looking at the function. Okay, so take a look at this graphic. We're introducing a new word here. The new word is inflection point. And I have two inflection points identified here. Okay. So, tell me if you can give me a definition of an inflection point. This is what I'm asking you to answer. An inflection point occurs where blank. Giving by those two pictures. We're making our own definition. Okay, everybody got it? Libby, you want to try it?
So yes, like words which is from upward and
Okay, be more specific. 'Cause it is a banned word here.
when x prime, when f of x, I don't know,
Okay?
never mind.
No, you're on the right. You're on the right track. Okay, I mean to pick on you there. Harry. Okay, you hear how he said that? Where f prime changes from increasing to decreasing or decreasing to increasing. Okay, that's one way that you can say it. Okay, that's a valid reason. Give me another one.
Would that be where f double prime is 0?
Yes.
I beat you to it.
So, the inflection point occurs where f prime changes from increasing to decreasing or decreasing to increasing. Can anybody say it in a less technical way? By looking at the graph. When does an inflection point occur? Yes? Okay, good. That's what I was looking for too. Wherever the function changes over from concave up to concave down or concave up to concave down. Concave down to concave up. Okay, as soon as it goes there. Oops, I forgot a word here. It's a very important word because it must be a point on the graph. It must be a point on the graph. It's possible to change from concave up to concave down, or vice versa, and not have an actual point. Can you think of a picture that it does that? How is it possible to have a function that changes from concave up to concave down, or vice versa, but it actually doesn't occur on a point? Okay. 1 over x, excellent. Okay, look at this. This is 1/2 of the y equals 1 over x function. Okay, is this concave up or concave down? This is concave up. Okay, this is concave up. Slopes are f prime is increasing, going from really super negative to close to 0. Always pick the extremes when you're trying to test something like that. Pick this point here and pick this point. Look at this. This slope is really negative. This slope is getting close to 0. Okay, that's a slope. The slope f prime is increasing. This point, this side of the graph, to complete the y equals 1 over x, this part here is concave down. Okay, it's concave down here. Is there an inflection point on this graph? And the answer is no. The reason is because this is a very important word. Okay? All right. So, the question is, how can we tell where the inflection points are and the concavity is? If we were just, say, given the function and we didn't even know what it looked like. It was just some wacky function. And so that's what we're going to do tomorrow. I'm going to teach you how we actually go about doing that. For example, if we had some weird function like this, okay, how do we tell what's going on in this one right here? Well, let me just point. Let's just see if you learned anything today. The function right here, let's pretend this is f. At any given point right here, on any given interval, how do we is this concave up or concave down? Up. That's correct. Okay. You tell me when it changes to concave down. Down there. Right here? Isn't that still increasing? Yes. At what point does it start to decrease? It's supposed to stop me right around now. This would be an inflection point because it goes from concave up to concave down. You see it? Concave up to concave down. That's where the inflection point occurs. Here it's concave down. Here's where it's concave up. Another inflection point. See that? Concave up. Then right around here is an inflection point where it goes to concave down for the rest. Can you see it? It's that moment that it switches from concave up to concave down. All right, we'll do all of the rest. I'll teach you the actual lesson tomorrow then. But you got the definitions down.